Hello, this is video 5 on Unit 5. We will start talking about nucleophilic attack to coordinated ligands. In particular, this video will deal with nucleophilic attack on alkenes, polyenes, and polyenyls. We have seen in the previous videos that in the case of reductive elimination and migratory insertion, reaction can occur between two ligands of the coordination sphere, therefore causing reaction between two organic fragments, resulting in an independent organic product once eliminated. In contrast, a metal can also activate a ligand so that direct attack of an external reagent can take place on the ligand without prior binding of the reagent to the metal. The attacking ligand can be either a nucleophile or an electrophile. In other words, the nucleophilic substitution and abstraction reactions can be viewed as ways of activation of substrates to allow an external reagent to directly attack the metal-activated ligand without requiring prior binding of the external reagent to the metal. The nucleophilic attack is favored when the metal fragment has an electron withdrawing character. It is a poor pi base but a good sigma acid, with the metal in a high oxidation state. For example, if the complex bears a net positive charge, or has electron withdrawing ligands, one of the ligands may be depleted of electron density to such an extent that can be attacked by a nucleophile. Examples of nucleophiles are methyl lithium, in which the methyl group bears a negative charge, hydroxide anion, etc. The electrophilic attack is favored when the complex has an electron donating character. It is a weak sigma acid but a strong pi base. For example, if the complex has a net anionic charge, a low oxidation state metal, and ligands that are good donors. The electron density of one of the ligands is enhanced by back donation so that it now becomes susceptible to attack by electrophiles. Examples of electrophiles are those in which the methyl group bears a positive charge, such as methyl chloride, the proton, the trityllium cation, etc. There are two possible modes of nucleophilic or electrophilic attack: the addition mode and the abstraction mode. In the addition mode, the reagent can become covalently attached to the ligand so that a bond is formed between the reagent and the ligand. In this case, the newly modified ligand stays on the metal. In the abstraction mode, the reagent detaches a fragment from the ligand, or even the entire ligand, in which case the modified reagent leaves the coordination sphere of the metal. A nucleophile abstracts a cationic fragment, such as a proton or methyl group bearing a positive charge, while an electrophile abstracts an anionic fragment, such as a hydrido or a chloride. Often, reaction with an electrophile generates a positive charge on the complex and prepares it for subsequent attack by a nucleophile. We will start having a look at addition reactions, starting with nucleophilic attack on alkenes, polyenes and polyenyls. Then, in the next video, we will go on with nucleophilic addition to the carbonyl group. Simple alkenes in the free state, such as benzene and ethylene, normally undergo electrophilic attack. They are not much susceptible to nucleophilic attack. Both benzene and ethylene become sensitive to nucleophilic and inert to electrophilic attack when they are complexed to a metal center. So, if we are interested in inhibiting electrophilic attack, we would regard the metal as a protecting group. On the other hand, if we are interested in promoting nucleophilic attack, we would regard the same metal fragment as an activating group. The nucleophile attack reduces in 1 unit the hapticity of the ligands to which it is added. Also, in the vast majority of cases, the nucleophile adds to the face of the alkene or polyene opposite to the metal. Since the metal is likely to have bound to the least hindered face of the free alkene or polyene, we may therefore see a selective attack to the nucleophile on what was the more hindered face in the free polyene. This is often useful in organic synthetic applications. As we have just seen, the nucleophiles tend to reduce the hapticity of the ligands to which they are added, since they displace the metal of the carbon in which the addition takes place. You've got in this slide 2 examples of nucleophilic attack. In this first case, although the oxidation state of the metal is 0, the fragment chromium tricarbonyl is electron withdrawing due to the backbonding from the metal to the good pi acceptor carbonyl ligand. The chromium tricarbonyl fragment activates benzene, making it sensitive to nucleophilic attack. The alkyl group from alkyl lithium bearing a negative charge attacks and adds to one of the carbons in benzene, affording a cyclohexadienyl ligand. In the second example, the metal is in a high oxidation state, that is iron 2, and also the complex has a positive charge. It is a cation. Therefore, the nucleophilic addition is favored. The methoxy anion will add to one of the carbons of ethylene, and the new anionic ligand, alkyl ligand, is formed. Please notice that in both examples, an anionic reagent is added to the complex, and therefore that negative charge coming from this ligand has to be taken into account. In the first example, we start with a neutral complex that becomes an anionic complex after the addition. In the second example, the starting complex is a cation that will become a neutral complex after the nucleophilic addition. Perhaps you are wondering why the methoxide anion, in this second example, attacks the ethylene group instead of the CP. Well, not all unsaturated coordinated hydrocarbons have the same reactivity. Green, Davis, and Mingos noticed certain patterns in these reactions, and from them devised a set of rules that usually, but not always, allow us to predict the site of addition. Rule 1 says that alkenes and polyenes, that is, even ligands, are attacked preferably to alkenyls or polyenyls, that is, odd ligands. Rule 2 says that open ligands react before closed ones. Rule 3 says that the attack preferably occurs on the terminal carbon of the ligand in the polyenes and open polyenyls. Rule 1 takes precedence over Rule 2 whenever they conflict. Let's see some examples. In the cationic molybdenum complex containing the following ligands: benzene, which is even and closed, butadiene, even and open, and allyl, odd and open, the nucleophilic attack will occur in exo on the terminal butadiene carbon. Let's explain why. The first rule indicates that an even ligand, benzene or butadiene, should be preferably attacked. The second rule says that the open butadiene ligand is attacked preferably to the closed benzene one. And the third rule states that a terminal butadiene carbon is preferred. In the following rhodium complex, the first rule does not apply in the absence of even ligand. The second rule gives preference to the cyclohexadienyl ligand, and the third rule to one of its terminal carbon atoms. These rules are meant to apply in the order Rule 1 before Rule 2 before Rule 3 to all cationic complexes, and they work most of the time, but remember, not always. In the mixed cation, iron Cp, eta6 arene, Rule 1 indicates that nucleophilic attack must occur on the benzene ligand, and it always does so. However, in the analogous hexamethylbenzene complex, the steric control dominates, and the preferred attack occurs on the Cp ligand, although Rule 1 gives priority to the arene ligand. Let us finally examine the nucleophilic attacks on the cations iron arene 2. The first attack gives a monocationic cyclohexadienyl benzene complex. The second nucleophilic attack can then occur either on the arene or the cyclohexadienyl ligand. When the arene is mesitylene, the rules seemingly work very well, since the even mesitylene ligand is attacked rather than the odd cyclodienyl, that is what the Rule 1 says. So, we have finished this part, and in video number 6, we will finish Unit 5. Thank you very much for your attention.